Hi, my name is Jim Young. I'm an applications engineer at ON Semiconductor, and today I'd like to talk to you about some solutions we've come up with for LED lighting. This particular demo features a high power factor constant voltage front end coupled to a buck regulator for the second side. The CV controller is an FL7740 that has a high voltage startup to maximize the capabilities of start while maintaining low standby power. This converter will maintain a power factor of greater than 0.9 at high line with half load. This is due to a dynamic optimizer that's inside that automatically compensates for the EMI filter phase shift. It maintains about 3% regulation under static conditions on the output voltage, and under dynamic loading, it's about 10%. This is far better than a lot of single-stage converters, which have a very slow compensation loop, and so it takes them longer to adjust to any dynamic change in either the input or in the output. The converter is operating in DCM, discontinuous mode, at 65 kilohertz. As the load is reduced, the frequency is cut back. This allows for higher efficiency operation at lighter load. Ultimately, in standby mode, the frequency can drop down to as low as 800 Hertz. With this configuration, you can achieve less than 300 milliwatts of standby power even at high line. It has cycle-by-cycle peak current limit. It has short circuit protection. And if the auto shutdown timer is activated, it's about 3-second delay, and then it goes through an auto restart. The operation of this is not limited to just LED applications. It would also be suitable for other CV outputs where you needed high power factor on the input. We followed this with a buck regulator. The buck regulator is able to maintain tight control of the LED current even with two separate strings. Perhaps you have one at one color temperature and the second string at another color temperature, and you're able to balance the two. The FL7760 is a continuous conduction buck regulator. It directly drives the output FET with a high current driver, and it can operate up to about 2 megahertz operation. Maximum about 60 volts input for the input line, and the LED current is directly monitored with a high side current sensor. This provides very, very tight control over the LED current that's flowing through the output. It has a dimming input pin. This dimming pin accepts a combination of analog and digital PWM type controls. This allows you very, very wide range operation, because while you're in a PWM mode, you can also adjust the amplitude to lower the output current and get a very, very wide dynamic range. The configuration of this demo board, we have a selector switch on these two independent buck regulators. We can select either analog input, where we're using, for in this case, a 1 to 10 volt input, or a PWM input. And I'll be demonstrating later independent control, where we can have one channel running in analog and one channel running in PWM. Here's the FL7760, which is in a TSOP6 package. And this is the switching FET that's being driven by the FL7760. Here we have the selector switch that decides whether the input is being derived from the analog dimmer or the PWM dimming, and that is available for each channel independently. Those outputs go over here to two independent strings of LEDs. We're providing our AC power from this AC source. We have a meter on each of the LED strings on the output, and this power supply is running a PWM oscillator that provides us with the PWM control. This is a conventional 1 to 10 volt analog dimmer that can also control the buck regulator. And here we have on the screen, this is showing the PWM signal that's being provided by this oscillator. So let's start off by turning on the AC power. We're running about 230 volts, and as you can see, our standby power is about 120 milliwatts. We'll turn on the analog dimming. Right now we have it set to both LED strings are being controlled by the analog dimming. And we can run the setting up to its maximum. For this instance, we have about 560 milliamps through each channel. If we run the dimmer down, we get down to, for this dimmer, minimum of 17 to 19 milliamps for the two independent strings. We have the capability to change the input. We're going to change one of the PWM dimming channels from analog to PWM. And now we can see on the screen, as I change the PWM duty factor, we can see the brightness of the LEDs changing, and we see the current through that string changing. So I'm going to turn off the analog control string, and I will focus mainly on this digital string. We can run that duty factor down to a very narrow level here. And right now we're running at about half a milliamp, which is 0.1% of our full current. At that point, we can see, we uncover the LEDs, there's just a very faint glow. We have the option now to actually reduce the amplitude of the PWM signal to achieve even further dimming results. So now we're down to less than 0.2 milliamps of current going through those LEDs. So it gives you a very, very wide range operation. Now we can increase this back up, and let's turn the analog string back on. And we see we have independent control of analog and PWM dimming for the two strings. So this is the FL7740 and FL7760 buck regulator, and thank you very much.